Good day, everyone. Welcome to another episode of CHE 101. I am Joven Jesus Reyes, here to discuss the term, specifically, Analysis of Thermodynamic Systems. To start, we must go over some key equations that we will use to analyze thermodynamic systems. The first of which is the law of conservation of mass, or the mass balance. The first term represents the difference between the mass of the two states, or two internal conditions. The second term represents the change in the mass due to flow rates, and this is equated to zero. The second equation is from the first law of thermodynamics, which is the energy balance. Do not be intimidated by this lengthy of an equation, since if we will break down each component, the first term is the change in internal energy, which is mainly due to the internal conditions of the system. The second term can be divided into three parts. First is a change in enthalpy, second is a change in kinetic energy, and the third is a change in potential energy. And these two terms is equated to the heat and the work. The last key equation is from the second law of thermodynamics, or the entropy balance. This may look very intimidating, but the first term represents the change in entropy due to the internal conditions, the second is due to the flow streams, and the third is due to the surroundings. This is equated to Sgen, or the entropy generated. And this whole thing may be greater than or equal to zero. And this will be equal to zero when the system is reversible. In some problems that involve the second law of thermodynamics, these isentropic efficiencies is sometimes calculated or it is given. For the term, four isentropic efficiencies are commonly used. One for turbine, one for pump, one for compressor, and one for nozzle. WAC represents the actual work done by the system. WS represents the isentropic work of the system, which is when the system is both adiabatic and reversible. And for nozzle, VAC represents the actual velocity of the system, while the VS represents the isentropic exit velocity of the system. Before we start analyzing problems, we can look at some common assumptions that we do in analyzing thermodynamic systems. For negligible potential energy, the term about potential energy is removed. For adiabatic, Q equals zero. For negligible kinetic energy, the term about kinetic energy is removed. For reversible, Sgen equals zero. Isentropic, which is the combination of both adiabatic and reversible, Sgen is equals to zero and Q equals to zero. For some gases that do not have data tables in Sontag, the assumption of ideality may be used if it is not specified that the system is a real gas. And the last common assumption is when the system is a controlled volume or it is considered a rigid vessel. This means that there is conservation of volume and V1 is equals to V2 and so on and so forth, which is equal to the total volume of the system. Let us have our first problem. A 100-liter rigid tank contains nitrogen at 900 Kelvin and 3 megapascals. The tank is now cooled to 100 Kelvin. What are the work and heat transfer for this process? In every analysis of thermodynamic systems problem, we must start with the given. Specifically, we must draw the system. So we have state 1, which goes to state 2. And then we will look at the given. So we know that V is equals to 100 liters, T1 is equals to 900 Kelvin, and P1 is equals to 3 megapascals or 3000 kilopascals. And we know that T2 is equals to 100 Kelvin. And then, now that we have the given and the diagram, we must write the required, which is the heat and the work for this process. Now, for our solution, we will start with the assumptions. And we will assume that potential energy and kinetic energy is negligible. And the system is also rigid as stated in the problem, which means that V1 is equals to V2 is equals to 100 liters or 0.1 cubic meter. Now that we have those assumptions, let us move on to the LCM, or the law of conservation of mass, which is M1 is equals to M2. Moving over to the first law of thermodynamics, since we don't have any flow streams and the potential energy and kinetic energy are negligible, our solution would be M2U2 minus M1U1 is equals to Q, and since there are no indications of work, we know that work is equals to 0, which is one of our required. Okay, so now we need M2, U2, M1, and U1. So let us first analyze state 1, which is at 900 Kelvin and 3000 kilopascals. If you would look at Sontag, V1 or the specific volume would be 0.09003 cubic meter per kilogram, and our U1 would be 691.65 kilojoules per kilogram. Now that we have the specific volume, we can divide the volume by the specific volume to get the mass. So 0.1 over 0.09003 to get a value of 1.11 kilogram. So let us add another slide for the continuation of the solution. So now that we know M1, let us move on to state 2. For state 2, the only thing that we know is that the temperature is Now that we know the values for M1 and U1, let us move on to state 2. The only thing that we know about state 2 is that temperature is at 100 Kelvin. However, we know from the law of conservation of mass that M1 is equals to M2. That means it is also 1.11 kilograms. And since it is a rigid vessel, V2 is also 0.09003 meter cube per kilogram. Since we know V2, we must now determine the state of state 2. And upon looking at the values, it is greater than the state at which it is a saturated vapor, which means that state 2 is superheated vapor. However, upon looking at the values, it is between 200 kilopascal value of 0.11520 meter cube per kilogram and 400 kilopascals of 0.05992 cubic meter per kilogram. That means we must interpolate the pressure to get our internal energy. And upon interpolation, which I will skip in this video, you will get a value of P2 of 291.06 kilopascals. And for the internal energy, the corresponding values are 71.73 kilojoule per kilogram for 200 pascals and 69.30 kilojoule per kilogram for 400 kilopascals to get a value for U2 of 70.62 kilojoule per kilogram. Now to have everything, let us just substitute it from the first law of thermodynamics or the energy balance to get our value for Q. So Q is equals to 1.11 times 70.62 minus 1.11 times U1, which is 691.65, to get a value of negative 689.34 kilojoules, which is our final required. For the second problem, a diffuser receives 0.1 kg per second steam at 500 kilopascal and 350 degrees Celsius. The exit is at 1 megapascal, 400 degrees Celsius, with negligible kinetic energy, and the flow is adiabatic. Find the diffuser inlet velocity and the inlet area. Just like in the previous problem, we will start with drawing the diagram. So the diffuser will be a trapezoidal shape with an inlet and exit stream. So the mass flow rate of stream 1 is 0.1 kilogram per second with a pressure of 500 kilopascal and T1 of 350 degrees Celsius, while stream 2 will have a pressure of 1 megapascal or 1000 kilopascals and a T2 of 400 degrees Celsius. So let's note that it is negligible kinetic energy and the system is adiabatic. So Q will also be 0. So for our required, let us denote U as the inlet velocity, so U1, and the inlet area, which is, let's denote as A. So for our solution, The law of conservation of mass would be m1 is equals to m dot 2 is equals to m dot, which is 0.1 kilogram per second. And for our first of thermodynamics, our energy balance, it will be m dot 2 h2 minus m dot 1 h1, which is from our change in enthalpy, plus 1 half m dot u2 squared minus 1 half m dot u1 squared equals 0. Since it is stated in the problem that the kinetic energy is negligible, we can cancel out the third term. And also, since all the masses are equivalent, we can also remove the mass from the equation to get an equation of h2 minus h1 minus 1 half u1 squared is equals to 0. So now let us analyze state 1, which is at 500 kilopascal and 350 degrees Celsius. So let us get the specific volume and the enthalpy for these parameters. So looking at the Sontag tables, V1 will be 0.57012 cubic meter per kilogram, and H1 will be 3167.75 kilojoule per kilogram. And then looking at state 2, which is at 1000 kilopascals and 400 degrees Celsius, H2 would be 3263.88 kilojoule per kilogram. So let's move on to the next slide for the continuation of our solution. So let us use our energy balance to solve for the inlet velocity. So 3263.88 times 1000, since we must ensure that the dimensions will be homogeneous across the equation, equals 3167.75 times 1000 plus 1 half u1 squared. Then we will use the shift solve function of our calculator to get a value of u1 of 438.47 meters per second, which is one of our required. So to solve for the other required, which is the inlet diameter, we will use the formula of mass flow rate, which is area times the velocity over the specific volume, which is also equivalent to area times the velocity times the density. Since we know the mass flow rate, the velocity, and the specific volume of the inlet stream, let us input our values of 0.1 is equals to area times 438.47 over 0.57012 to get a value of area of 0.00013 meter squared or 1.3 centimeter squared, which is the answer for this problem. A piston/cylinder receives R410A at 500 kilopascal and compresses it in a reversible adiabatic process to 1800 kilopascal and 60 degrees Celsius. Find the initial temperature. In this problem, we will now focus on the use of the second law of thermodynamics. But first, we must start with the diagram of this problem. Since it is a piston or cylinder, let us draw a simple piston setup, state 1, which will be converted to state 2. And we know that state 1, P1 is equals to 500 kilopascals, and P2 is 1800 kilopascals, and T2 is 60 degrees Celsius. And the process is reversible, which means Sgen is equals to 0, and adiabatic, which means Q is equals to 0. So R required is the initial temperature, or let's say it. So R required is the initial temperature, which is T1. To start, our assumptions would be the potential energy and kinetic energy would be negligible. And it is stated the system is reversible, which means Sgen equals 0, and adiabatic Q equals 0. For our material balance, the law of conservation of mass would be M1 is equals to M2 is equals to M. And for our first law of thermodynamics or energy balance, M2U2 minus M1 U1 will be equal to W. But the focus on this problem will be on the second law of thermodynamics, which is delta S is equal to the integral of dq over t plus S gen. Since the process is reversible, S gen is 0, and it is adiabatic, dq over t will be 0. Since both terms will be 0, delta S will be 0, or S1 is equals to S2 once you transpose one to the other side. Let us now analyze state 2 since the parameters in this state are complete. So we have 1800 kilopascals and 60 degrees Celsius. So looking at Sontag, we will get S2 at 1.1076 kilojoule per kilogram Kelvin. And based on our second law of thermodynamics or entropy balance, this is also equal to S1. So now let us look at state 1, which the only parameter that we know is that it is at 500 kilopascals. We will now look at the values at 500 kilopascals through which the entropy is equal to 1.1076. However, it is between two values. At the value of negative 13.89, which is the saturation temperature, the entropy value is 1.0647, and at 0 degrees Celsius, the entropy value is 1.1155. So we must interpolate to get the temperature at which this entropy value occurs. We will get a value of T1 is equals to negative 2.16 degrees Celsius, which is our answer for this problem. In the previous problems, we focused on what happens when either there are internal conditions or there are input and exit streams. But what if they are combined into one problem? So we will now look at transient processes or when there are both internal conditions and input and exit streams. So for our last problem, ammonia is stored in a 100-liter tank with quality of 3% and an initial temperature of 25 degrees Celsius. From an external source, heat is transferred into the tank to raise its temperature and pressure. When the maximum pressure is reached, a safety valve opens and saturated vapor at 100 degrees Celsius escapes. It was determined that 10 kilograms of saturated ammonia vapor was released by the tank. Calculate the total heat transfer, maximum pressure, and the quality of the tank when the valve is open. In problems like these, it is important that our diagram is correct. So to start off, let us write our given. So let us assume this box is our system. So we have state 1, which we know that the volume is 100 liters or 0.1 meters cubed with a quality of 0.03 or 3% and a temperature of 25 degrees Celsius. It is an ammonia mixture. And we also know that our valve is closed. Let's label that stream E. And it is also stated that heat enters the system. So this is our state 1. Let us now draw state 2. State 2, we still have the heat. However, our valve is now open with an exit stream that we know is a saturated vapor with an exit temperature of 100 degrees Celsius and a mass of 10 kilograms. We also know that the temperature of state 2 is 100 degrees Celsius. So now that we have this whole diagram, let us write our required, which are Q, the heat transfer, P2, which is the maximum pressure or the pressure at which the valve opens, and X2, which is the quality of state 2. To start our lengthy solution, we will of course start with our assumptions. Since no data about them are given, potential energy and kinetic energy are negligible in this problem. Also, the tank will be assumed to be constant volume, which means that V1 is equals to V2 is equals to V of 0.1 meters cubed. Okay. So let us now write our balances. So for our mass balance, it will be M1 is equals to M2 plus ME. So we don't have an MI in this mass balance since there are no input streams. And for our first law of thermodynamics, or energy balance, it will be M2U2 minus M1U1, which is due to the internal conditions, plus MEHE, which is due to the flow streams, which is equal to Q. We don't have a W since the tank is constant volume. Let us first analyze state 1. We know that it has a quality of 0.03 and a temperature of 25 degrees Celsius. Since we know the quality and temperature, we can use these values to get the specific volume and the specific internal energy of state 1. For V1, our formula would be 0.001658, which is the volume at saturated liquid level, plus 0.03 times 0.12647. 0.12647 is the difference between the specific volumes of saturated vapor and saturated liquid, and these values are taken from the Sontag tables. To get a value of 0.005452 cubic meter per kilogram. And since we know our specific volume, we can now get our M1, which is 0.1, which is our volume, over our specific volume of 0.005452 to get a value of 18.34 kilograms. As for our other value, our U1, we can use the same formula as V1 to get our value, which is 296.59 plus 0.03 times 1038.4 to get a value of 327.74 kilojoules per kilogram. So we now have two of our unknowns, or for our formula. Let us now analyze state 2. For state 2, the only thing that we know is that it is at 100 degrees Celsius. So using our mass balance, M1 is equals to M2 plus ME, which we now have values for both M1 and ME, we can solve for the value of M2 to be 18.34 minus 10, which is equal to 8.34 kilograms. Since we know that the volume of 0.1 cubic meter is constant, we can get the specific volume for state 2. So V2 is equals to 0.1 over 8.34 to get a value of 0.01199 cubic meter per kilogram. And if we will look at the values at 100 degrees Celsius, we will know that state 2 is a saturated mixture. And since it is a saturated mixture, we know that pressure, or P2, would now be 6,253.7 kilopascals, which is one of our required. And since we now know it is a saturated mixture, we can now compute for the quality using our quality formula. So 0.01199 is equals to 0.002188 plus x2 times 0.1565 to get a quality, or x2, of 0.6263 or 62.63%, which is now our second required. And now that we know the quality, we can now also compute for U2. So 686.96, which are values taken from the Sontag tables as mentioned before, plus 0.6263 times the difference of 618.4 to get 1074.26 kilojoule per kilogram, which we will use later in our calculations. And for our last state, which is our output stream E, we know it is at 100 degrees Celsius and it is a saturated vapor. So what we need is the enthalpy. Looking at the Sontag tables, we will get a value for enthalpy at 1416.9 kilojoule per kilogram. So now that we have everything, let us use our energy balance of Q is equals to M2U2 minus M1U1
plus MEHE. And let us substitute our known values of 8.34 times 1074.26, which is for stream 2, minus 18.34 times 327.74, which is for stream 1, plus 10 times 1416.9, which is for our exiting stream. To get a value of Q of 22,527.88 kilojoules, which is also equal to 22.53 megajoules, which is our last unknown and our final answer.
That marks the end of our latest episode of CHE 101. If you have any questions, you may email the chen.acads Gmail or message the Facebook of the Chen Acads Hub. Once again, this is Jovin Reyes. Thank you for watching.